Okay, so today I'm going to look at differentiating power series. Okay, so let's just suppose that the power series from n equals 0 to infinity of c sub n times x to the power of n, which is, if you plug in 0, you get c sub 0 times 1 plus c sub 1 times x plus c sub 2 times x squared, and it keeps on going and going and going. And we're going to assume this converges to some interval that we'll call I. Let me straighten that up to look more like an equal sign. Now what if we let this part, we just call that our f of x. So if f of x equals that c sub 0 plus c sub 1 x plus c sub 2x plus c sub 3x and so forth and so on and so on, then f prime of x, the derivative of a constant is 0, so that disappears. So you have c sub 1, and that x kind of vanishes. Uh-oh, forgot my cubing. Yeah, I would have eventually ran across that one. Kind of helps. Okay, so you have your c sub 1, then your c sub 2 is here. And differentiate this term, you just bring down your 2 and subtract 1. You have your c sub 3, bring down your 3 and subtract 1. And it keeps on going and going and going. Where your f prime of x actually becomes the sum from n equals 0 to infinity, n times c sub n, x minus a to the n minus 1. Clear that up a little bit. So if you look at it, all you really did was your original power series. Just like with any other derivative for the power rule, you brought down the n, subtracted 1. The only difference is here you have in kind of the general form with the x minus a. But for this particular one, we have it where a is equal to 0. Okay, so that's kind of how the power rule came about. So now we'll give sort of a general definition.
No, don't mind me.
Okay. Let's bring that up a little bit. Differentiation of a power series. So this gives all the little details and everything. This is just sort of a broad overview. Uh-oh. Suppose that the sum from n equals 0 to infinity of c sub n, and instead of xn, we'll make it the more general x minus a to the power of n, converges, not to, more on the interval, say a minus r and a plus r. Remember that r is your radius of conversion. For some r greater than 0. Okay. Now if it converges on that interval, then it also means it's differentiable on that interval. And f of x is differentiable on a minus r, a plus r, where your f prime of x is equal to the sum from n equals 0 to infinity of n c sub n times x minus a to the power of n minus 1, which is equal to, which we found out up there, c1 plus 2c2x plus 3c3x squared plus, and so forth and so on and so on. But now that's actually differentiable for the interval, the absolute value of x minus a. Oh, sorry, is less than r. Okay. Now the only thing that kind of changes a little bit is the fact that this lets us know that it's differentiable from the open interval from a minus r to a plus r. We still don't know about the endpoints. So you have to plug the endpoints in separately and find out whether or not they converge or not. Okay, so the radius of conversion is the same for f, let's say f of x and f prime of x. But the, oh, sure. But the, no problem. Interval of conversion, endpoints, may have, I was going to say different behavior. So really all we're doing is once we find out the interval of conversion, we pretty much are just testing to see if we're going to use parentheses or brackets. That's really all this does. All right, any questions on that so far?
Is R just any real number?
Oh yeah, R is just any real number, any positive real number. So next we're going to look at integrating our f of x, which is really the same thing. We break it down and we integrate each term. Okay, so remember that we have the sum from n equals 0 to infinity of c sub n times xn is equal to c sub 0 plus c sub 1 times x plus c sub 2 times x squared, etc., etc., etc. And it converges on some interval that we'll call I. Okay. And from that, we took that as our f of x. C sub 0 plus c sub 1 x plus c sub 2 times x squared. I'll go c sub 3 x to the third, and so forth and so on and so on. Okay. Now if we took the integral of each one of those terms, that would just equal our lone constant. The integral of that would just become c sub 0 times x plus c sub 1 times x squared over 2 plus c sub 2 times x to the third over 3 plus c sub 3 times x to the fourth over 4, and so forth and so on and so on. And at some point, you're going to have a plus c. Because we integrated, so we can't forget about the plus c. Okay, so all I'm going to do is just move the c over here. So c plus c sub 0 x plus c sub 1 x squared over 2 plus c sub 2 x to the third over 3, and so forth and so on and so on. Okay, so that's kind of the same thing, kind of a general, not a general idea, but kind of a broad introduction to it. So the general definition, integration of power series, is what if we suppose that instead of x to the power of n, we're going to have x minus a to the power of n, since it's the general description. So c sub n times x minus a to the power of n converges on the interval a minus r, a plus r, for some real number r greater than 0. Where the absolute value of x minus a is less than r, which really just gives us that. Oh, sure. Okay. Then we know that f of x is integrable. I hate saying that word.
Degradable?
No, integrable. I know, integrable. On a minus r, a plus r interval, and the integral of that f of x with respect to x is what we just figured out up there. C plus c0x plus c2x squared plus c... Oh, did I miss one? Yep, I skipped c1. I knew something didn't look right. c1x squared over 2 plus c2 x to the third over 3, and that's so forth and so on and so on. So really, this just means the integral of f of x is equal to c plus the sum, because we're just going to get all of this and bring it together, from n equals 0 to infinity, of c sub n times x to the n plus 1 over n plus 1. Okay. And once again, this tells us that the endpoints might or might not converge. So we'd have to test them. Or may not converge. Oops. So I'm going to buy stock in pencil leads the way I go through these things. All right. Any questions on this one? Leave that up for a few seconds. Move this over here.
So does this just mean that within the interval itself, we can just kind of differentiate a function as it would be if it were not a power series with its elementary integration?
Well, it's more along the lines of if you know the integral or the derivative of a power series, you can find out the power series for that derivative, or the integral, depending on which one it is. So if your f of x is natural log of x, then you can find the power series for 1 over x just by differentiating the power series for natural log of x.
Okay.
Does that make sense?
Yeah.
No. Okay. All right. So for our first example, first we're going to just find the power series because it kind of leads up to where we're going. find a power series for f of x equals 1 over x centered at 1. Okay. Okay. So what if we write f of x equals 1 over x in a over 1 minus r form? Okay. Kind of turn it into a geometric series, or the sum of a geometric series. So our 1 over x, we can make that equal 1 over 1 minus negative x plus 1. That would just be 1 plus x minus 1. Okay, so if it's in the form a over 1 minus r, your a is equal to 1. Now I'll put that over here. And your r is equal to negative x plus 1. Okay, so that means if we have our 1 over x, which is equal to the sum from n equals 0 to infinity, since we put it in geometric series form, that's a times r to the power of n. That means this is going to equal the sum from n equals 0 to infinity. A is equal to 1, so we can just leave that as 1. R is equal to negative x plus 1, so we'll make that negative x plus 1 to the power of n. Okay. And the reason we put it like that is because now, sum from n equals 0 to infinity, let's say if we decide to factor out that negative 1. So if you have negative 1 times x minus 1 to the n. Okay. So since you have two factors, you can just get that n exponent and kind of distribute it to both. So you have negative 1 to the nth power times x minus 1 to the nth power. Okay, so that's going to equal, if you plug in n equals 0, you get 1. If you plug in n equals 1, you get negative x minus 1. And clean that up a little bit, looks a little bit blurry. So this term is n equals 0, this term is n equals 1, plus n equals 2, that becomes positive, that becomes x minus 1 squared. N equals 3, you have negative, x minus 1 to the third, and it keeps on going and going and going. And we know this converges at the absolute value of x minus 1 is less than 1. If you just did the power series. I mean, not power series, the, what is that called? The ratio test. There we go. So this just means that negative 1 is less than x minus 1 is less than 1. So if we add 1 to all three terms, you have 0 is less than x, less than 2, or the, well, they didn't ask for it, but the interval of convergence is just 0 to 2. Okay, so we have our power series that we figured out. And yeah, put it right there. Okay, so that's our power series for 1 over x. All right. So any questions on that one? All right. Leave that up for a few more seconds. Yes.
Oh, for the answer on that, would we have to break it down Distributing the n to the -1, or manipulating it all in parentheses.
I know for some of them they were multiple choice. That's why I kind of showed you how to do that way, because sometimes they'll have options where you just have the negative kind of oscillating. So at least this way, if they ask for it, you know how to convert it over. Yes.
Okay, so the absolute value is our a minus r, right?
Yes.
Is a just our function of x? And then would our r be just any other constant?
For that one, your r would actually be your function of x. Your a is usually just a constant. So kind of depends on how the problem is set up.
So for this one, what is our a minus r? That's what I'm looking at.
Say a minus r? Or are you thinking of the 1 minus r? Yep, let me grab that one. Oh, wrong one. Ah, this is it. There we go. Okay, let me bring that down. Okay, you said a minus r, all right?
I'm not sure.
A
Oh,
minus r
x minus a is less than r. Is maybe what I'm looking at. But I don't know if that's what we're talking about here.
Oh, x minus a is less than r. That's just your a is equal to 1. So x minus 1 is less than 1. This is when we use the ratio test.
Right. So our a is that 1
Mm-hmm.
because it's the constant, or like
Uh,
why is our a 1?
Oh, here, because that's
Oh,
what we
just
took it
the
out
zero
earlier.
series.
Yeah. So if you had like a 1/2 up here and you factored that 1/2 out to the front, then that would have been your a.
Okay.
That make sense?
Yeah, what is our r then?
Oh, your r. Right after we pretty much kind of manipulated this one to being the a over 1 minus r, this is our a over 1 minus, we were able to make this our r.
Okay.
All right. Now, a little bit of trickery sometimes. All right. Any other questions on this one? All right. Okay, so for our next example, let's say if we want to find, not the power series, but a power series, 'cause I'm sure there are more than one. Find a power series for f of x equals natural log of x, centered at 1. Okay. Now the one thing we already know, that 1 over x is equal to the sum from n equals 0 to infinity of -1 to the nth power times x minus 1 to the nth power, which is from the previous example. Okay. So that means our natural log of x is equal to the integral of 1 over x with respect to x. Okay. Which means this could equal the integral, since this 1 over x is equal to this power series, this is just going to equal the integral of this power series. -1 to the n times x minus 1 to the nth power. Yep, with respect to x. Okay, so we know this is just our constant. So that -1 to the n doesn't really change, that stays the same. Okay, so this is equal to the, let me see, that makes it, nope. let's say, where is it? Here we go. The sum from n equals 0 to infinity of -1 to the nth power. It's going to be x minus 1 to the nth power, n plus 1 power, over n plus 1, plus c. Okay, so instead of figuring out natural log of x, all we had to do was take the derivative of natural log of x. Since we know that, we just use that to find out the power series for natural log of x, without having to go through all that trouble. Okay. And let's say if we decide to solve for c. Sometimes they'll have you solve for c and say, okay, let x equal whatever. Then you can find an exact power series. So we'll just let x equals 1. Like I said, just because it's completely random value. But if they wanted you to do it, they'll tell you what they wanted x to equal. Okay, so if x is equal to 1, that means that the natural log of 1 is equal to the sum from n equals 0 to infinity of -1 to the nth power times 1 minus 1 to the nth plus 1, which automatically becomes 0, which is why I picked 1, plus c. Okay. So this just becomes 0. And natural log of 1 is 0. So c is equal to 0. Okay. So that means our natural log of x is equal to the sum from n equals 0 to infinity of -1 to the nth power. Bring that up a little bit. Times the sum. Oh, we already put the sum. Equal 1 to the nth power. Where did I leave off? X minus 1 to the n plus 1 over n plus 1. Or, if you wanted to, it could equal the sum from n equals 1 to infinity of -1 to the n plus 1 times x minus 1 to the nth power over n. Because if you look at it this way, if you plug in 0 here, -1 to the 0 power is 1. X minus 1 to the first power over 1. Here, if you plug in 1, -1 squared is also 1. X minus 1 to the first power over 1. So just starts off at 0 and 1, but you have the same result. Okay. Now this actually comes, oh yes.
So you would, you don't include the c anymore?
Nope, the only reason we took the c out is because we made x equal 1.
We found that c equals 0, so doesn't that?
Oh.
We found that c
Oh,
equals
that-
0.
Oh, yeah.
Doesn't matter.
Yeah,
That's the only reason.
Yeah, that's it.
But if it wasn't 0.
Oh yeah, if they gave you a different x value, then yeah.
Or if c ended up being 4 or whatever.
Yeah.
Just keep it in
Yep, then you just keep it in. All right. So any other questions on this one? Oh, yeah.
So where you put the n plus 1 is interchangeable between those two?
Oh, you mean for these two?
Yeah.
Oh, only if you change your index.
Okay.
So here, if you change this from n equal 1, you can just make that n. Because if you plugged in 0, it would be x minus 1 to the first power. And here, if you made it equal to 1, x minus 1 to the first power. So when that index changes, it kind of switches up a little bit. All right, so we're going to use this. So if you have